Hey, what's up, Calc 2 crew, and welcome to the Daily Problem Sets. Hey, it's still me, Corey. Let's go ahead and talk a bit about cylindrical shells, the cylindrical shell method, and finding volumes. And this is going to be something similar to what our plight was back when we were talking about the washer and disk method. However, the way we go about finding volumes is a bit different. And if you remember with the washer and disk method, we were really trying to build out the different solids that we had. I like to think of it sort of like that carnival game with the bottleneck and the rubber ring. And if you go ahead and keep sort of stacking those rings over and over again, and there's obviously some more nuanced detail to it, that you can build out some surface that way. However, with the cylindrical shell method, it's a bit different. And I think I like to think about maybe 3D printing or something like that when I consider this method, though that might not be how every 3D printer actually prints. Do I own a 3D printer? Not yet, but I'll make the claims that I'm making right now in this video. With the cylindrical shell method, it's more like taking, for example, soup cans and superimposing soup cans on soup cans. We sort of build out the surface that way, and we have different radii and height that end up sort of building out what we're doing. And in general, the formula in general for our volume is going to be the integral from a to b 2 pi times the radius times the height. And this could be with respect to x or with respect to y. I'll just put a dx here, but we'll certainly be able to talk about when we're going with respect to x, when we're going with respect to y as well. Now keep in mind, you should have already watched the lecture videos. This is just a little bit of extra for us to test what we already know. And feel free to pause the video and try the problems on your own. That's really the best way to go about it. So let's use the method of cylindrical shells to find the volume of the solid obtained by rotating the region bounded by xy equals 5, x equals 0, y equals 5, and y equals 7. And we're rotating that about the x-axis in this case. Hey, let's get a visualization. Let's see what's going on here. So I can start with my axes. X-axis, y-axis. Y equals 5 and y equals 7. So let's say y equals 5 is here, and y equals 7 is here. So y equals 5 is going to be a horizontal line at 5 units. Y equals 7 is a horizontal line at 7 units. X equals 0, we know that's just a funny way of saying the y-axis. And now I want to know what xy equals 5 looks like. And I'm going to do that in the blue, the baby blue. Now I could go ahead and start by saying, well, when y equals 5, x times 5 equals 5 means that x is 1. So that would mean x is 1 and y is 5, so it gives me a point there. But what about when y is 7? So when y is 7, I get x times 7 equals 5, or that x is equal to 5/7. And this is actually less than 1, right? 5/7 is less than 1. So this would bring me up here, but maybe sort of like there. And then I want to connect. So here, connecting these two, it shouldn't be a linear function. If I actually solved this for y, if I think that would be helpful, we would say that y is equal to 5 divided by x. There's going to be some small curvature to it, but for the small sort of piece that we get, it might not be as important to necessarily have to depict that, but that's the truth of the situation. Now, like I mentioned before, sometimes we go through and get these rough sketches just to find out that it kind of makes it difficult to see anyways. I would maybe want to exaggerate this a bit. I can work with this picture the way that it is for sure, but just for the sake of clarity before rotating and getting fancy with this, let me try to do this a bit better so that I can see more of what's going on. This will be my y equals 5. And then this will be my y equals 7, or if you have like a pencil, you would probably just erase. This is my y-axis, my x-axis. And then my curve in blue, I don't really want to change it, but it was very small the way I had depicted it. So I'm going to have to exaggerate this in an egregious way. Let me say x equals 1 is all the way out here. Crazy to say that, but hey, I'm crazy, so get used to it. And then 5/7, I'll say, well, maybe 5/7 is like here, just so I can see more of it. So this is definitely not drawn to scale, but for clarity's sake, I can get a better idea as to how my region looks. So bounded by y equals 5 and y equals 7. Here I have my curve xy equals 5, also in the blue, but now everything's blue. And then we said that x equals 0, or the y-axis, was another bounding curve. So I get this sort of interesting looking region. And we said we wanted to rotate this region about the x-axis. So I like to do the rotated region in red. And here the x-axis is acting as my mirror. So I have this sort of 5 units of space that I want on either side. I'll try to get this looking hopefully reasonably. And then something like this. Yeah. And then like this. Looks good enough for what we're going to need it for. Because now I want to draw in a typical cylinder, and I want to be able to determine what the radius and the height is going to be dictated by. Now, I always want you to do this the same way. In this case, since we're rotating about the x-axis, we're going to be sort of looking at it on the side, sort of looking at it like this, sort of, hurting our neck a little bit. And when I draw in the radius, I want to do that in my original region to start. I do want to try to mimic it in the rotated region, but we're always going to be referencing the original shaded region, which is in blue for me. And then I can draw the top of the soup can, like this. And then from the axis of rotation, which is the x-axis, that should be the center, and I want to draw my radius out to that original region as well. There's my radius. And this shouldn't quite go too far, but it should sort of stop at that curve in blue, really. And here I have a typical cylinder, and I can draw more of these. I can bring the wall in a little bit closer. I can bring it out a bit further and get another depiction of it. Let's maybe do one more in purple, just since we're already here. You've already clicked on the video. I want to move this out a bit more, sort of closer to y equals 7. Get something like here, and then I can mimic it in the red. I can draw the top. So I'm going to have a soup can in purple. I can draw my radius out. So we see how this is going to sort of look or behave. We sort of stack these, we superimpose them to build out the solid, in this case, with the shell method. Now I want to know what the radius and the height are going to be dictated by. Now the height, so again, I'm sort of like, I'm like hurting my neck looking at this, got my head on its side. The height of it is going to be dictated by the wall of the cylinder. And here I have this wall. It's starting at the y-axis and going up until it hits this curve. So we'd say, well, okay, so what is that dictated by? It's dictated by this curve. So the height is given by the curve that we had. And what was that? Well, that was x times y equals 5. Now we're going to have to pick one of these variables to work with, but let's wait on that because I want to talk about the radius next. The radius, so here we're starting at the center and we're going out until we hit the wall, of the cylinder, and that is going to change, right? It's going to change, and every time that we do that, we're going up some arbitrary vertical distance and we're stopping, and it's going to be somewhere between 7 and 5, or between 5 and 7, however you want to sort of phrase that. And that's important to keep in mind. So the way that we would label the radius in this case, the radius is given by y. It's just this generic vertical movement that we have, and that y is going to be between 5 and 7. And it's going to make every stop along the way. It's going to be 7, it's going to be 5, and it's going to be everything in between 5 and 7. But so the radius is just going to be some generic movement in that vertical direction. Now that I see this, we'd say, well, okay then, so really we should be integrating with respect to y. The radius is going to take on the value y, and that's going to be bounded from 5 to 7. So right away we get an idea as to how we're integrating, what the bounds of integration should be, and this also tells me how I should be solving my function. Right, so since the radius is given as y, and y is from 5 to 7, then the height, my function, xy equals 5, I should solve that as a function of y. So I got to solve it for x in this case. So I'd say, well, okay, we divide by y, so x is 5 divided by y is what we get for the height. So we have radius is y, height is 5 divided by y, and we can set up our integral. We go back to the traditional yellow for the stylus. We want to integrate. We said y goes from 5 to 7, so integrating from 5 to 7, it's 2 pi times the radius, which is y, times the height, which is 5 over y. And here we're integrating with respect to y. So there's our setup. Once we get to the setup, and setup is everything for these sections. For the washer disk method, for cylindrical shell method, the setup is really what we're talking about. Once we have it set up, it's now just an integral, which we've done integrals before. So focus a lot on the setup. Draw these pictures out. Really think about what you're saying. Think about what you're doing. That's going to be the key to our success here. We have the integral from 5 to 7. 2 times 5 is going to give me 10 pi. And I want you to notice that y over y cancels. So we just have 10 pi dy to integrate. We can integrate that. It's a constant. We integrate the constant. It just generates that variable back. So 10 pi y. And that's from 5 to 7. And then I can evaluate this. So 10 pi can come along as the coefficient. I can leave that factored out. Plug in 7 for y, plug in 5 for y, and then subtract in between. So this one's not so bad, right? It gives me 10 pi times 2, or it's going to give me 20 pi for the volume, using that cylindrical shell method. Let's take a look at another example. So I'm going to use the method of cylindrical shells to find the volume V of the solid obtained by rotating the region bounded by the curves y equals 8 times square root of x, y equals 0, x equals 1, I'm rotating about the line x equals -3. So not one of the principal axes. Here I'm using x equals -3 as my axis of rotation. And let's see if we can get a picture here. Okay, doesn't seem so bad. So it's my x, my y-axis. What do we have? We have y equals 0. Now y equals 0 is going to be the x-axis. We have x equals 1. Let me say x equals 1 is out here. Give myself enough sort of room to breathe. X equals 1 is going to be this vertical line. And then we have y equals 8 times square root of x. Now this is the square root function, but it has this coefficient of 8. And let's say, for example, when x is 1, then y is 8 times square root of 1, which is 8 times 1, which is 8. So it should be up 8 units. Let me say 8 units is maybe up here. It's going to intersect there, but then otherwise it's going to be that square root function. So I just sort of stretched out a bit, but same idea, square root function, like this. We said this is maybe 8, for example. Okay, not so bad. So then I want to rotate this. So I have my region dictated by, here we have y equals 0 is the x-axis, x equals 1 is this vertical line, and then y equals 8 radical x is this curve in blue. I want to rotate this about the line x equals -3. Okay, sounds fine. So I'm not going to do this to scale. You know, I'm not trying to make you angry. I just got to make sure I can fit this into the space that I have. But let me say -1, -2, -3. And this is my axis of rotation. X equals -3 is this vertical line. But then I'm going to want to do some more of these markers because I have this space leading away from my original region. I want to do that on the other side as well. So do that like this, like so. And now I can think about rotating this region. Remember, we don't have our nose pressed against the mirror. We got some space. I want to mimic those units of space on both sides. So my original region is right here, and then I have 1, 2, 3 units of space. So on the other side of my mirror, my dotted line at x equals -3, I need 1, 2, 3 units of space. And then from there, I can try to mimic this as best as I can. I get my rotated region in red. There's my rotated region. Now I want you to notice, and this is different than the previous example, and we can try to generalize these a bit. What do you think? She's here to help. We can try to generalize these a little bit. In the last example, let's go back to it. We rotated about the x-axis. The x-axis is a horizontal line, and we wanted to integrate with respect to y. Now, in this example, we are rotating about a vertical line. We're going to want to integrate with respect to x. And that's something that you can just sort of keep in mind as you're going through these examples. I think it can be helpful, which is why I'm mentioning it now, that we start to notice these sort of tendencies for the different kinds of setups that we get, and then how we can expect the rest of it to look. But from here, let's go ahead and draw in a typical cylinder. I want to start in my original region, which is with the blue, and I can draw the wall of the cylinder. So these cylinders are going to be soup cans facing upward, so I don't have to hurt my neck trying to look at them. There's the wall of the cylinder. I want to try to mimic that in the rotated region. And then I want the top of the soup can. You can draw the bottom of it too, but I don't all the time because I'm a bad person. Just kidding. I like to have fun. And there is my soup can in purple. And I want to go right to the middle, put a little point there, and I want to draw my radius. My radius is going to go out. And I want to draw this to the original region, the wall in the original region. And there I have all the stuff that I need to start talking about what I need to talk about. Let's talk about the height. So the height, when I think about the height of these, and I can draw more of them, but the height is going to be dictated, it's going to use shorter ones, taller ones, it's going to be dictated by this curve in blue. So the height is always going to be given by the function y equals 8 square root of x. What about the radius? Now the radius is tricky here. We like to think about these in terms of generic horizontal or vertical movements. In this case, it's a generic horizontal distance that we're considering. But if I go to this original region, and if I go to the wall in the original region, then I would say this is some arbitrary horizontal distance that I'm traveling. But before I go and label it x, I want to keep in mind that this would only be from the y-axis out to this wall. So it always has to be sort of relative to one of the principal axes. So if I go from the y-axis out to the wall of my cylinder, I can call that a generic distance of x. Okay, so that seems fine, but that's not all that my radius is. My radius has this other piece to it as well. This other piece that I'm missing is, it comes from this -3. It's from my axis of rotation, but think of it as a distance. It's 1, 2, 3 units of distance. So this entire radius, I want to sort of depict it up here a bit, it's 3 units out, and then it's that arbitrary horizontal distance of x as x moves from 0 to 1. So this entire piece is really a 3 plus x or an x plus 3. So we'd say that the radius is given by x plus 3. And it can be tricky to get the handle on this. So what I would say is always think about first labeling that arbitrary vertical, or in this case horizontal distance, and that always wants to be keeping two things in mind. The principal axis, in this case, we're talking about from the y-axis, and that's going to be then to the wall of the cylinder in the original region. So always think about the wall of the cylinder in the original region. The distance that is away from the principal axis is going to be what you're labeling, in this case, x, or if this was flipped around, we would talk about y as a distance from the x-axis. So keep that in mind, and then from there, you might have to add something, you might have to subtract something, you might have to subtract constant minus a variable, something like that. But as long as you have a clear picture, as long as you're sort of following these generic rules and ideas, you're going to be able to figure it out. If you have any issues, let me know on the discussion board, and I'm here to help you. I want to see your picture. I want to help you figure out what the radius and the height is given by. The radius can be tricky. If it's not a principal axis of rotation, the radius can be tricky. But that's what we're here to talk about. Because once we have the setup, it is just an integral, and there's nothing too crazy about that. But let's go ahead and see if we can set this up now. Now in this case, we're going to be stacking these soup cans out in a horizontal fashion, and that's going to be going, if we're looking at the original region and thinking about that wall, because we're already rotating it, so we just think about the one wall, it's going to be moving from 0 to 1. So we have bounds from 0 to 1, and it's 2 times pi times the radius. The radius is x plus 3 times the height, which is 8 square root of x, and we should be integrating with respect to x. And this is our setup. We're ready to start thinking about integration. Well, okay, so let's multiply the 8 and the 2 and bring that out. That's a 16 pi that I can bring out as a coefficient. The integral from 0 to 1. But I still have x plus 3 times square root of x. Or I'm actually going to write square root of x as x to the 1/2 power. Going to help me out with integration, right? So what do I have here? I have 16 pi in front, and then I have the integral from 0 to 1. Let's distribute. X times x to the 1/2, think of it like x to the first. I'm going to want to add the exponents, so that's going to give me x to the 3/2. And then plus, here we have 3 times x to the 1/2, so that's 3x to the 1/2 with respect to x. And okay, so now we're ready to integrate and then hopefully evaluate. So I have 16 pi in front. X to the 3/2, if I integrate this, remember using the power rule, I want to add 1 to the exponent and divide by that same new number. So that's x to the 5/2 divided by 5/2. And then plus 3 times, when I integrate x to the 1/2, same idea. It's going to give me x to the 3/2 divided by 3/2. And that this is from 0 to 1. And I do want to clean this up. I don't want to divide by fractions. I want to multiply by reciprocals instead. So I have 16 pi. Here, instead of dividing by 5/2, we should multiply by 2/5, x to the 5/2. Plus here, instead of dividing, so I said this 3 still, instead of dividing by 3/2, I want to multiply by 2/3. And then x to the 3/2. And then this is from 0 to 1, of course. And then notice that the 3's are going to cancel. So I just have 2x to the 3/2 for that last term. Now I want to plug in my upper bound, plug in my lower bound, and subtract in between. It's going to leave 16 pi factored all the way out in front. When I plug in 1 for x, I get 2/5 times 1 to the 5/2 plus 2 times 1 to the 3/2, and then minus. When I plug in 0, I get 2/5 0 to the 5/2 plus 2 times 0 to the 3/2. And I can evaluate this. So 16 pi factored all the way out. 1 to the 5/2 is 1, so I have 2/5. Plus 1 to the 3/2 is 1, so then 2. And then minus 0 to the 5/2 is 0, 0 to the 3/2 is 0. 2/5 times 0 is 0, 2 times 0 is 0, so all of this is just 0 for the lower bound evaluation. And looks good so far, right? So what can I do? I can just go through the rest of the arithmetic, you know, get a common denominator. So 16 pi I have 2/5 plus 2. If I multiply by 5 over 5 is 10/5. So 16 pi times 12/5. And I can go ahead and multiply this out. So we'd say, okay, 16. So I would keep the pi here, and I would do funny arithmetic like I always do. 16 times 10 is going to give me 160, plus 16 times 2 is going to give me 32, and then all over 5. And then that's going to give me, if I want to add this up, that's going to give me 192 pi over 5. Not so bad. You multiply how you like to multiply. I'll multiply how I want to multiply. And we're still going to be on good terms. And we like to box it. We like to star it because we are done. Let's take a look at one more example for the shell method. Let's do the setup only. And we'll talk strategy from there, and we'll move on. I'm going to use the method of cylindrical shells to find the volume V of the solid obtained by rotating the region bounded by the given curves about the specified axes. So you have the region bounded by x equals, we have parentheses y minus 5 squared, and x equals 4, and we're rotating this about the line y equals 3. Okay, doesn't sound so bad. Let's see if we can get a bit of a picture going. My axes looking perfect like they always do. My x-axis, my y-axis. And we have one of the bounding curves is x equals 4. The other is x equals y minus 5 squared. Now I would want to know where they intersect. Right, so I would say, well, maybe we want to start by setting these equal. So 4 equals y minus 5 squared. I can take square roots of each side, but keep in mind that when I introduce the square root, I really need that plus or minus going on. So we'd say square root of 4 is going to give me 2, but it should really be that plus or minus 2. So we'd say this gives me two possibilities. 2 equals y minus 5, and negative 2 equals y minus 5. Another way to think about it is I could be squaring a 2 to get a 4, or I could be squaring a negative 2 to get a positive 4. So I get this sort of two values I want to work with. And we solve for y from there. If I add 5, 5 plus 2 gives me 7. Here if I add 5, 5 plus negative 2 gives me 3. So these intersect at y equals 3. So let me get a scale here. So I'll say this is 1, 2, 3, 4, 5, 6, 7. And let me, I don't usually do a scale, but when I do, I like to do it in Calc 2. 1, 2, 3, 4, 5. That's probably good. 6, 7. Might not need all of it, but better to have it not need it than need it and not have it. And so we have also the line at x equals 4. So 1, 2, 3, 4. In the x direction, there's my line x equals 4. And I want to draw also the curve y minus 5 squared. I'll do that in the blue. But we know that at y equals 7 and y equals 3, it's going to intersect with this vertical line at x equals 4. So y equals 1, 2, 3, it's going to intersect. And then 4, 5, 6, 7, it's going to intersect. And then all I really need maybe is one more point to get an idea as to how this looks. If I look at the function, if I'm trying to think of an easy way to do this, I could say, what about when y is 5? When y is 5, I'm going to get x is 5 minus 5 squared, which is 0 squared, which is 0. So when y is 5, x is 0. So 1, 2, 3, 4, 5, x is 0. And now sort of the mystery is done, right? I know this is going to look, if I sort of get my crude drawing here, it's going to look like this. And it's going to keep going, but since it's bounded by this curve at x equals 4, I really don't need sort of that extra overhang. But just to get an idea as to how this is going to look. So this is my region, bounded by these three curves. I have sort of this little excess to it. Let me let me sort of trim it down. I wanted to show it for just a bit, but I don't want you looking at it because it's not what we're talking about. And we have our axis of rotation is going to be at y equals 3, which is this horizontal line at y equals 3. And I want to rotate this region. So now this is one of those cases where we're looking at the mirror, but we got our nose against the mirror. So there's no space. We're lined right up with it. But I want to try to mimic this as best as I can. So I do intersect here at the y-axis, but I have 1, 2 units of space doing that. So on the other side of the mirror, I have 1, 2 units of space, and then right against the mirror should be there. And then I have 1, 2 units of space, and I'm back up at the line x equals 4. So I have to be careful because my axis is also a unit of space. So 1, and then 2, and then I should be back there, and then I can draw this as such. There's my rotated region. Okay, so far so good. Now I want to think about how a typical cylinder would look for this. And these, so notice we're rotating about one of these horizontal lines. We have the line y equals 3. So we're going to have to sort of, look at these with our head tilted. This is the one that's going to hurt my neck a bit. And I can draw in my typical cylinder. I want to start in the original region. Everything should be relative to the original region. There's the wall of the cylinder. I want to mimic this in the rotated region. And I want to, here I could do the top and the bottom of the cylinder. I'm not trying to avoid doing that. And I want to draw in the radius. Now the radius is going to go from the axis of rotation and then out until we hit the wall of the cylinder in the original region. So always referencing that original region. Let's talk about the radius first. I think the radius can be tricky. Let's talk about what we said already. Let's apply it here. I have this sort of arbitrary vertical distance that we're considering, but keep in mind that has to be from the wall of the cylinder in the original region. There's the wall of the cylinder in the original region relative to one of the principal axes. In this case, it has to be the x-axis. So we'd say this distance here is some arbitrary vertical distance. This is what we call y. Has to be from the wall of the cylinder in the original region to the x-axis. Got the wall of the cylinder in the original region to the x-axis. We call that arbitrary y. It's some distance y. However, this is much too much. I don't quite want that. I'm only interested in this piece in the green, which is from the wall of the cylinder to this dotted line in red, which is my axis of rotation. This is what my radius should be. So what do I not want here? Well, I don't want all of this garbage from my dotted line in red, my axis of rotation, to the x-axis. But what is this? How much space is this? This was the line at y equals 3. This is 3 units of space. 1, 2, 3. We got 3 units of space. So if I want my radius, well, it certainly isn't y, but y is part of it. The piece of it that I don't want is this 3. So we would be able to say that the radius is r equals, it's y less by 3. It's y minus 3. So not so bad, hopefully. Hopefully that makes sense. If not, let me know on the discussion board. We'll get it squared away, cleared up. Okay, but what about the height? Now for the height, we want to look at the wall of the cylinder. And we say, well, the height's going to change as we bring it in sort of closer and further away. But it does rely on, well, there's a couple things going on here. It relies on this curve that we have, and that curve was the function y minus 5 squared. But it also, and this can be sort of deceiving if we're not paying attention, it also relies on x equals 4. And if we think back to area between curves, section 6.1 that we talked about, we really want to think about upper minus lower, or in this case, rightmost minus leftmost. So if I'm labeling the height correctly, it's not maybe what we think about at first glance. We immediately notice the curve is playing a role, but it's actually both of them. The height, let me know if this makes sense to you, is given by, it has to be the function x equals 4 minus, right? It's upper minus lower. It's between these two. It's between these two functions, 4 minus this y minus 5 squared. Maybe if I finish this in the baby blue, it's a bit easier to see that the height of the cylinder, that sort of wall that I have in green, it's not just one of the curves, it's bounded between both of them. The curves y minus 5 squared, y minus 5 squared, and then x equals 4. Bounded between these two. So it's trapped between those two. So whenever I draw it, it's going to, start at one and stop at the other. So I really want to think about the difference between those two. And I want upper minus lower, in this case, rightmost minus leftmost, like we talked about in 6.1. So the height is given by this 4 minus, and then the other function y minus 5 squared. And I got to use parentheses there. Okay, I think then we're ready for the setup, and we said setup only for this one. The integration, it's between y equals 3 and y equals 7. So it's going to start at y equals 3, and it's going to keep doing it until it gets to y equals 7, and all the while rotating around the axis of rotation to build out our solid. And we can set this up. So the volume, the integral from 3 to 7, 2 times pi times the radius. We said the radius is y minus 3 times the height, which is 4 minus quantity y minus 5 squared. And this integration is going to be with respect to y. There's a lot going on here. Before I just leave you with the setup, I want to talk a bit about strategy. Bring the 2 pi in front. It's a coefficient. Don't forget about it, but it's not going to really play a major role in the calculus. The height is going to be tricky. What I want you to do with the height, I want you to FOIL the y minus 5 squared. I want you to distribute the subtraction and make sure you distribute that subtraction and collect the like terms. You're going to have some like constants. You're going to have an inner and outer term you can combine. And then you're going to want to multiply out again with this y minus 3. So it's going to be a lot of algebra. Just be careful with it. Be patient. And from there, you should be able to integrate, evaluate, should be successful with that. But we said setup only for this one. Well, let's go on. Let's talk about some other stuff. You've got an extra page here. Keep up the great work. You're amazing. Keep it up. Some exclamation points. Get a smiley face. Should have had one. Now we got one. Now let's talk about some examples from 6.5. And here we're talking about the average value of a continuous function. For this, we would want to just integrate over the region. And then we want to divide by the length of that region. So divide by b minus a, or I like to have a coefficient 1 over b minus a. Okay, so let's go ahead and talk about this. So we'd say the average value, I want to find the average value of the function 4 times cosine to the 4th times sine, and that's from 0 to pi. So right away I can set this up. The average value should be given by, I want to integrate the function on its region, so that's from 0 to pi. I want to integrate 4 times cosine to the 4th times sine with respect to x. But then I want to divide by the length of the interval. So I should be multiplying by 1 over pi minus 0. And then I can clean this up. Pi minus 0 is just pi, so it's a 1 over pi, and I can bring the 4 in front. So we could say 4 over pi, and then the integral from 0 to pi of cosine to the 4th times sine, and then with respect to x. Now to integrate this, we're going to want to work with a substitution. So a U substitution back from section 5.5. And for this, the way we want to do it, pause the video, let me know what you think, yell it at your computer screen. I want to pick my substitution on cosine because it has that exponent of 4. So we're going to say let's let u be equal to cosine of x. The derivative then of this du, derivative of cosine gives me negative sine of x dx. And I do have a sine of x dx, not a negative 1 though, so we multiply both sides by negative 1. So negative 1 du is equal to sine of x dx. And we transform this integral. Now, I'm not going to change bounds. I'm going to back substitute and get the old bounds back. Can you change bounds? Sure. It's probably proper to do so in this case as well. The reason why I don't like to ever change my bounds is because I think that with substitution, the back substitution is an important part of that. Because if we don't have bounds, if we have an indefinite integral, then if we forgot that step, we would have an answer that isn't quite complete. And so I like to keep everything, I like to teach in one way if possible. I want to make sure that you're not neglecting a piece that you may be needed. But change bounds if you want to change bounds. I'm not going to do it. I'm going to back substitute because I think the back substitution is important. We can argue about it on the discussion board, of course. I'm always available for that. So I'm going to say here I'm integrating from, I don't know what the new bounds are, and if I'm not changing them, then I'm not really bothering. So I'm just going to call it some bound u sub 1 to some bound u sub 2 because it is still a definite integral. But instead of cosine to the 4th, I have u to the 4th. And I'm replacing sine of x dx all with a negative 1, use parentheses I guess, and a du. And this integration is not bad. So we can do this. I'm going to bring the minus sign out to join my coefficient. So negative 4 over pi. And if I integrate u to the 4th with respect to u, I get u to the 5th divided by 5. And this is bounded, but if I don't change the bounds over to this new sort of placeholding variable, then I don't know what they are. But it's okay because I'm going to back substitute anyways, and I'm going to get my old bounds back when I do. So let me bring the 5 out to join the pi. So I still have negative 4 over 5 pi. And instead of u to the 5th, so I have u to the 5th, but what did I say u was? I said u was cosine of x. So I'm going to back substitute. I'm going to re-replace u by cosine of x. So instead of this u to the 5th term here, I have cosine of x all to the power of 5. And as soon as I do that back substitution, I return to my old bounds on x, which were from 0 to pi. So it isn't so bad. Now I can evaluate. So I have this negative 4 over 5 pi all in front. When I plug in pi, I get cosine of pi, and that's to the power of 5, minus, when I plug in 0, I get cosine of 0, and that's to the power of 5. And now I can evaluate. So here I have negative 4 over 5 pi. You say, well, what is cosine of pi? Cosine of pi, hopefully we know that 1 is negative 1, that's to the 5th power, minus, what about cosine at 0? That's positive 1 to the 5th. I can work through this a bit more, almost done. Negative 4 over 5 pi. Negative 1 to the power of 5 stays negative, negative 1. And then minus 1 to the 5th is 1. Almost there. We have negative 4 divided by 5 pi times minus 1 is minus 2. Negative times negative is positive. 4 times 2 gives me 8 over 5 pi. And that is the average value of this continuous function for cosine to the 4th times sine on that interval from 0 to pi. We have the average value of that continuous function. Okay, so not so bad. Let's take a look at another one. Let's find the average value of the function 3 times square root of x on the interval from 0 to 4. And we're going to show that this satisfies the mean value theorem for integrals. Okay, not so bad. So let's go ahead and take a look at it then. So let me start by first finding that average value. We would say here the average value is going to be, I want the integral from 0 to 4 of my function, which is 3 times square root of x, but I'm going to write that as x to the 1/2, 3 times x to the 1/2. But then I have to correct it, making it an average value by multiplying by 1 over 4 minus 0, or dividing by the length of that interval. And I can go ahead and clean this up. I can bring the 3 out. 4 minus 0 is 4, so 3 over 4. And then if I want to integrate this as well, we would say integrating x to the 1/2 gives us x to the 3/2 divided by 3/2. And this is from 0 to 4. I don't want to divide by a fraction. Instead, I want to multiply by a reciprocal. So we have 3/4 times 2/3 times x to the 3/2 from 0 to 4. And if I clean this up, the 3's are going to cancel. 2 divided by 4 reduces to 1/2 x to the 3/2 from 0 to 4. And I can evaluate this. Of course I can. I would like to. 1/2 can stay in front. If you want to leave it attached, that's fine. I don't like babysitting these coefficients, so I wouldn't. And then I can plug in 4 for x, so I get 4 to the 3/2. Minus, I can plug in 0 for x, that's 0 to the 3/2. And then I can go from here. So I have 1/2. I'll skip over this first part. 0 to the 3/2 is just 0. With 4 to the 3/2 power, working with these fractional exponents by hand doesn't have to be a nightmare. Think of it like re-raising. So 4 to the 3/2, I can think of it like 4 to the 3 to the 1/2 power. I can sort of break it up and say, well, if I'm re-raising, I'm multiplying these anyways. 3 times 1/2 is 3/2. But the trick, for me at least, is thinking about the fractional part of it first. You can do it this way. It's not the end of the world either, but it's just going to make it, I think, a bit more difficult because you're going to get a larger number before you make it smaller. So I would prefer to think of this as rather 4 to the 1/2 and then to the power of 3. Just sort of taking advantage of the fact that we have this nice commutativity of multiplication like this. 3 times 1/2 is the same as 1/2 times 3, so no difference. But 4 to the 1/2 power is really a square root, right? 4 to the 1/2 is square root of 4, which is 2. And I got to cube it, and that gives me 2 cubed is 8. So here we have 1/2 times 8 minus 0, or 1/2 times 8, where that gives me 4. So my average value is 4. Now it says, show that this satisfies the mean value theorem for integrals. What does that mean? Well, hopefully you're watching the lecture video, but let's go and let's talk about the mean value theorem when we saw it in Calc 1. The mean value theorem for derivatives says that f prime at c is equal to f at b minus f at a over b minus a, which is saying that if I have some average rate of change on an interval from a to b, then at some point in that interval, in the interior of that interval between a and b, my instantaneous rate of change had to have been equal to my average rate of change. And that would be for a continuous function. If I make a replacement on this, let's say replace f of x by big F of x, and here we're thinking about an antiderivative, I want you to notice that big F prime of x is just little f of x. Again, thinking about antiderivatives. Then we would get the following useful result. We would say, first we would start by saying, okay, so this is now big F prime at c is equal to big F at b minus big F at a, all divided by b minus a. And here big F prime is just little f, regular f, so little f at c is equal to, but this capital F at b minus capital F at a, we can think of that as a definite integral. We could say this is the integral from a to b of the function f of x dx over b minus a. And this, by definition, is our average value. So we're saying little f at c is equal to our average value. So what this mean value theorem for integrals is saying is it's saying that there must be some value in the interval where the function, so f at c, in this case, must be equal to 4 for some value c in the interval. Okay, what was my function? My function to start with was 3 radical x. You can replace it with c. I don't usually do that. We call it c at the very end. I think that's fine. So I'd say my function, 3 radical x, should be equal to its average value. And I think this makes sense when we think about average values for continuous things, like temperatures. If you find the average temperature over 24 hours, sometimes it's hotter, sometimes it's colder. At some moment, it should have been that temperature. Temperatures don't really jump. It might seem that way in Buffalo, but, it should be continuous. So you'd say, well, if the average temperature today is supposed to be 60 degrees or something like that, then probably at some point outside the thermometer is reading 60 degrees, is the idea. And let's see if we can solve. Let's see if it's true. So I can divide by 3. So square root of x is equal to 4/3. I can square both sides. So x is equal to 4/3 squared, or that's going to give me 16 divided by 9. And this is what we're claiming that value c is. So let me call it c now. Say c for Corey, is 16 divided by 9. And this should be somewhere in the interior of the interval that we're working with, and that interval was 0 to 4. And so the question is, well, is this in the interval from 0 to 4? Yeah, right, it is, right? This number is greater than 0, it's positive, but it is smaller than 4, right? It's smaller than 2 if you want to sort of get picky with it. But yeah, it's somewhere between 0 and 4. So this is our value. So our average value is achieved on this interval for the function, and it happens at the value 16/9. Not so bad, right? Let's take a look at one last example for this section, and then we're going to yeet on out of here. We want to find the average value of the function 4t times e to the negative t squared on the interval from 3 to 7. Let's set it up. We know how to set these up. I want to integrate from 3 to 7. I want to integrate my function, which is 4 times t times e to the negative t squared. I want to integrate with respect to t, but I have to correct this and make it an average value by dividing by the length of the interval, which is 7 minus 3. Or I like to do multiplying by 1 over 7 minus 3. Okay, well, what do we get? 7 minus 3, that's just a funny way of saying 4, so 1/4. Integral from 3 to 7, 4t, e to the negative t squared dt. And this looks nice because my 4 and my 1/4 should cancel. So I get the integral from 3 to 7 of t times e to the negative t squared dt. Now to integrate this, I'm going to want to work with my substitution method. Let's do pink. For my substitution method, go ahead and try this one out, pause it, resume it when you're ready. Hey, welcome back. Substitution method, we got it. We're going to let u be equal to negative t squared. If I take the derivative, du gives me negative 2t dt, and I can see the t dt. I have the t dt, but I don't have this negative 2. So we would say, well, divide both sides by negative 2 or multiply by negative 1/2. So I can then say, well, then negative 1/2 du is the same as t dt. And I can make these replacements. And you know I don't like to change the bounds over. If you like to change the bounds over, do it. I know what you're doing. I'm not upset by it. It's just not. I like to back substitute. Does it make a difference? Not really. I bounce from u sub 1 to u sub 2, whatever those are, I don't care. And let's make our replacements. Instead of e to the negative t squared, I have e to the u. And I'm replacing the remaining t times dt with a negative 1/2 du. But this integral looks a lot nicer, and I certainly can integrate it. So we'd say negative 1/2 comes along as the coefficient. If I integrate e to the u with respect to u, that gives me e to the u. And since this is bounded, I don't need my constant. But now what I want to do is I want to back substitute so that I can get those old bounds back. So we'll say, sure, negative 1/2 is my coefficient, and then e to the u. But what did we say about u? We said u was negative t squared. So I'm going to re-replace u with negative t squared. And as soon as I return to that original variable t, I get my bounds on t back, which were from 3 to 7. And now I can go through the evaluation. I'm going to leave this -1/2 factored out in front. But then I want to plug in my upper bound for t, my lower bound for t, and subtract in between. So that's e to the negative, we got 7 squared, and then minus e to the power of -3 squared. And what's that going to give me? I have -1/2 in front, and then e to the negative, and then 7 squared is 49, minus e to the -3 squared is 9. And you could leave your final answer like this. You know, if it were me, I wouldn't probably bring the 1/2 in, but I might bring the minus sign in just to clean it up a little bit. And bringing in the minus sign is going to flip the sign on everything in here, which is really going to just reverse the order of the subtraction. I can actually show you the result really quick so you don't think I'm making this stuff up. But if I just have arbitrary values like a minus b, and I have this minus sign, I want to bring it in, it's going to give me -a plus b, which is the same as b plus -a or b minus a. So I'm just going to sort of bring in the minus sign and then flip the order of the subtraction. Classic trick. So +1/2, I have e to the -9 minus e to the -49. I just think this looks better aesthetically. Does it matter? No, of course not. Let's, what do we want to do? Got a final answer. Let's box it. Looks good. Star it. Hope you're feeling good about the average value of a continuous function. Thank you so much for your time. Don't forget to be taking a look at the homework. Make sure you're doing the homework for the sections. And let me know what questions you have for me over on Piazza. I'm here to help. I want to help you. But so I will see you next time. Remember, no matter what you're doing, to keep learning, keep dreaming, and always follow your heart. I'll see you next time. All right, take care for now.